Okay, so we have to have some periodic solution in order for to make physical sense, and so we then intuit that ml squared has to be positive, and so this whole quantity has to be negative. Okay, and then again, what that implies is that we get oscillatory solutions, and so normally we would write this as a constant times e to the I m phi plus another constant times e to the minus I m phi. And you'll see that, in fact, the constant doesn't matter because remember we have a theta. We have the theta part of the wave equation 2, the theta part of the Schrodinger equation 2, which we're going to solve, and we might as well just combine the constants all together. Okay, so we don't need to worry about the constant, and we don't need the negative I m phi solution because as you'll see, what we have is our allowed solutions include plus and minus I m phi. Okay, and so basically the way that we have this one number m, okay, m sub l. This is m sub l, okay, and we need, that's our one constant. We need to determine its values, or its allowed values, okay, and so we basically have to have continuity. That is, when we go around the azimuthal direction, okay, in by one rotation, that is, when phi goes to phi plus 2 pi, then the wave function has to be equal to itself there. It has to meet smoothly. And so the condition is that e to the iml phi plus 2 pi is equal to e to the iml, which since we have a sum of in the exponent here, then we can write that as a product of different exponents. So e to the iml phi times e to the iml times 2 pi, and this has to be equal to the value of big phi at the angle phi, so e to the iml phi. Okay, so now we see that this equation can only hold if this, okay, this term is this term here is equal to 1. Okay, excuse me. So e to the iml times 2 pi has to be equal to 1, which you can very easily show to yourself that implies that this number, this constant ml, can take on the following values: 0, plus or minus 1, plus or minus 2, plus or minus 3, corresponding to e to the I. So it could be e to the 0, so 1. It could be e to the e to the I phi, e to the 2 I phi, etc. Okay, so that's our how we so we found now that by from the azimuthal equation that we get quantization. We get a quantum number ml, okay, and it's quantized, meaning that it has only certain discrete values that are allowed, and so we'll see what that means in a second. Okay, so if we think about, if we go back to Bohr's model for the hydrogen atom, recall that there we assumed that the electrons were orbiting in some circular orbit with radius r, okay, and that was some multiple, the radius, that circumference of that orbital was some multiple of the wavelength, okay, of the electron wavelength, so the de Broglie wavelength, which we know to be h over the momentum, so h over m v, and v phi here is just the tangential component of the momentum. That is velocity. That is the motion around in a circle. Okay, and so we can rearrange this equation as ml times h, Planck's constant, is equal to 2 pi r times m v phi, and so we see that ml h bar is equal to m v phi sum r.